Hi, good morning, everyone. I just started the recording and I'm still admitting people to the class. We got about 20 people. Let's see when we reach to about 25 and then we can start. Meanwhile, yeah, if you have any comments, questions, yeah, it's a good time to raise the question, unmute the microphone until a few more people join us. Bright space is obviously functional, and I am adding the class content for each class to here. Probably you guys already know about that. So for this class, I have the newer slideshows here, and also a SAP 2000 example that we may or may not get to it today. And for previous sessions, you even have the recording of the lecture. So you guys can go back, or if you are sick, etc., you can watch it later on. And here in the under course tools, I started groups. So 10 groups are defined there. I'm not still very fluent with using this, but I realized that group number 4 is already taken. So 4 people have registered for group number 4, which is very good. Thanks a lot. So yeah, it looks like I did it correctly. So it is working. Other teams, please also start like adding your name, pick a number that you like the best, and then have like 3 people or 4 people in your team. If I go to class list, statistics. So we have 32 learners. That will make a nice 8 teams of 4. So definitely like talk to each other, or I mean, you guys are 4th year, so you know each other. Create your teams, and if there is a challenge, let me know, and I will try to address it. And yeah, the other day I asked that the teaching assistant Behnam is also added to this course. They had forgotten about him. And now he has better access to the whole content of the course. So I think, yeah, I think this bright space site is functional. If you guys have comments, again, either tell me or email me. But looks like everything is working as I wanted. Now we are 23-ish and 11:05, so that's fine. We get started. Sometimes a few students show up a few minutes later. Here's the course outline and course schedule again. And we are at 17 May today. Next week, in about 1 week, I expect you to send me, or I think it should be through Brightspace. So you just upload your draft work plan to Brightspace for Teams. So you guys have about 1 week to form up your team and have a quick discussion and decide about the topic from the suggested ones or other topics, or even email me or email Behnam and ask what we suggest or etc. So just create your team, write a draft work plan for us by about Friday next week, and upload it to the Brightspace. That should be not too difficult. As you see, even submitting the draft work plan has 10 scores out of 100. So don't skip it. If you jump into final work plan, then you will lose 10%. I'm trying to really convince everyone to work with a schedule, and you will be very happy by about mid-July because you have done everything for this course. That's about the outline and the schedule. And I think we didn't finish this one. Let me see if I can make it full screen. Yeah, I'm using 2 screens today, so the microphone and the speaker has changed, but I'm not seeing anybody objecting, so I think I'm audible. You guys are hearing me. For full screen mode here, and it's shared. So last time we tried to just talk about the basics of dynamics of structures, probably the most important slideshow right in front of you for most of the term. We covered the basics. We talked about the stiffness, mass, equivalent lateral load, and why the solution is sensible. What do we mean by free vibration? How can we use the outcome of a free vibration test, whether it's like experimental test or numerical modeling test? For both of them, this works to obtain your period and also your damping, which are very important parameters. Real life experiments. And what if we have ground motion excitation, which is earthquake? Harmonic excitation, it's important and a useful tool, a little bit more advanced tool, but useful, using half power bandwidth to, again, estimate your period and damping. Okay, I think we stopped right here, numerical time integration. So a lot of times there is no closed form solution for the real world problems, whether it's earthquake or shaking of a structure. And on the other hand, like we are, myself and the newer generation, we are becoming too lazy to try to learn and understand the closed form solutions, and we prefer the computer tools, which are mostly based on numerical time integration. We are becoming lazy, but we cannot be too lazy because we cannot produce wrong results and blame it on computer. We are in charge of correctness of the solution. So there are some basic concepts in numerical modeling. The idea of the idea of time stepping. Time stepping means discretizing the excitation using time steps. So if you look at this plot here, we have the excitation, which could be force or base acceleration, and it's a function of time. We try to look at its variation in small time steps, so that's what we call time stepping, using time steps. And at each time step, we apply the load to the system, to the whole structure. And we basically in a way note down the response. So this curve is showing the response, which is say deflection or velocity, acceleration, forces, etc. We note down the response at the end of each time step, and the response at the end of the following time step is dependent on, say, characteristics of the structure, forcing function, and also on the previous response. So the previous response parameters like U1 is the initial condition to calculate U2 at the end of the current time step. Solve for response at each time step. Interpolation of excitation. Now, what we are talking about is that we have a curve of acceleration or a curve of forcing function, which is P. However, we are discretizing it, so we are really paying more attention practically to the values T at Ti, which is Pi, and at Ti plus 1, which is Pi plus 1. Therefore, we should have some assumption about how P or acceleration changes in between. And that assumption really affects the accuracy of the results and the outcome of the analysis. So that's something to think about even when you are using computer software to do this task for you. So basically, actually, the forcing function was changing like this, but maybe it was even more harsh and it had a very rapid change, huge change between Pi and Pi plus 1. But in most of the modeling assumptions, we assume that it linearly changed between Pi and Pi plus 1. But we should be aware of that. Interpolation of excitation is efficient for linear system. Approximate the variation of the excitation between the time step by a line. So we are using a line here. And use the closed form solutions developed for linearly varying excitation. That could be a solution. Just use the closed form solutions from books for a forcing function that is linear and apply it to a linear system and determine the deflections through time. That's the typical linear solution that we could obtain from textbooks or any book. And then use this, or apply this solution at every time step, which is, we said here that it has high efficiency or accuracy for linear systems. Then we have the central difference method. In the central difference method, basically, this is our assumption here. So when you have deflections through time, which you can record or calculate, we want to know how it's related with velocity. So prime, U prime indicates velocity, and U with 2 dots indicates acceleration. And we use a simplified or naive, not naive, but simple assumption based on engineering judgment in a way. How can I measure velocity, the average velocity between 2 points? Again, there are equations for that. So note that this is like between U3 and U1. So between U3 and U1, you try to use U3 and U1 to basically calculate the velocity at U2. And therefore you have 2 time steps here. And similarly, you can work out the acceleration. We had the equation of motion. I mean, if somebody follows this slide in one session, you should be fresh. They should be fresh on this. And they can just insert this approximation of velocity and acceleration into equation of motion. That's the inertia term, which was mass multiplied by acceleration. And this is the damping term, which is the damping coefficient multiplied by velocity. And this is the stiffness term, which is say a stiffness multiplied by deflection. And then these are the resisting forces, and they should be equal to the external force. And then you can work out this equation. It has one unknown. If you have, say, already determined ui and ui minus 1, then you can go one step further and determine ui plus 1. That's the benefit of discretization. So you can solve for, you already have u0 and u1, you calculate u2, and then you move on and calculate all the deflections. So your computer program basically does that behind the scene. And what you need to really know is that if you have set, or if you have decided to use a software that uses central difference method, there is a stability requirement. So your solution won't be stable if your delta t, your time step, is larger than certain value. You should meet these stability requirements. I mean, it happens that you run a solution and you see that it becomes unstable through time and you have to debug it. Maybe you come to this slideshow and check if there is central difference method, then I should check my delta t only for stability. And then for accuracy, then obviously use the smaller time step is normally better. And then there's this other method, which is called for discretization, which is called the Newmark's method. And again, you have approximation of this time velocity based on acceleration and displacement based on velocity and acceleration. So again, you want to have only one unknown instead of having three unknowns, which are velocity, acceleration, displacement, because your equation had all three of them. You reduce it to only one unknown using these two equations. Again, you have a stability requirement. So that's something to be aware of, that different methods have different stability requirements. Yeah, so I tried to, or last year when I edited the slideshow, I tried to keep it simple and high level. Obviously, as engineers, we don't want to go into a lot of details on these math equations, except if it's other research. You guys can pick your research even in this area, but we need to have high level awareness, especially as we are all using computer software. And sometimes we are surprised or even shocked by seeing the results that don't make sense and or are unstable, diverged, etc. There are two. Okay, so let's go back one step. So you see that the stability requirements for Newmark is dependent on gamma and beta, that we can decide about them. We can decide about gamma. The solution is dependent on gamma and beta, and the stability requirement is also dependent on those parameters. You can use different assumptions. You can assume that the acceleration between two time steps remain constant, like you read a value here and you read a value here, but then you really use an average of the two, which is called constant average acceleration. And there is another assumption, which is linear acceleration, meaning that the acceleration really changed linearly between the 2 points. And so for this one, in order to achieve constant average acceleration, you have to pick gamma is equal to 1/2 and beta is equal to 1/4. And if we go back here, 1/2 minus 2 times 1/4 is 0 like denominator. And this whole thing is infinite. So it means that it's always stable. That's what we call unconditionally stable. So this solution is like it appears to be more approximate, but the benefit is that you don't need to worry about the stability, but you focus on accuracy and you reduce time step to achieve accuracy. Similarly, for linear acceleration assumption, different values of gamma and beta, and it's not going to be unconditionally stable. You're looking at the same equation, 1/2 minus 1/3. So it has some value. You can calculate that. So we saw a case where we had unconditional stability. Yeah, now how to use this knowledge for SAP 2000, which is our software, preferred software is for this course. I copied this from CSI knowledge base, and the recommendation was that for well-behaved problems, we recommend using the Newmark method with beta is equal to 1/4, which uses the constant average acceleration method. So the suggestion is to use unconditionally stable solution by the owner of the software or creator of the software vendor. For poorly converging nonlinear time history cases, however, whether it's like a solution, like a structure with a lot of nonlinearity and you have a difficulty obtaining converged solution with the solution number 1, then you go for solution number 2, which is Hilbert use Taylor method and use alpha between 0 and minus 1/3. So that's that I just copied it from their website. And this solution, we didn't really go through it, but that's the recommendation from the website. Note that all nodes should have mass and rotational inertia may be added to improve dynamic response. This is also should be noted that in dynamic analysis, generally we are dealing with mass and stiffness, so don't forget to add mass to all nodes. Even if, like in this software, in this particular software, if you have a negligible mass, just use a very small number rather than 0, because the software requires that all nodes have mass. That's for your dynamic analysis numerical solution using SAP 2000. Now, introducing a very important solution in structural engineering. It used to be super important. I consider it still very important, although like nowadays with very fast computer systems, everybody, including myself, wants to jump into numerical integration, but still for understanding the structural response well and for back checking the response, we use response spectrum. And also you need to understand, kind of have a good understanding of response spectrum to understand the simplified solutions from the from like National Building Code of Canada and other codes, which in their mindset is based on response spectrum solution. So let's first see what is a response spectrum curve. So assume that you have an earthquake happening and you want to create a response spectrum for that earthquake. As I said, earthquake, we normally, structural engineers at least, we know earthquakes as acceleration records. Now, assume that you have your earthquake and you have a tool, say SAP 2000, and you want to know what is the response, like just naively build up your response spectrum curve. What would you do? So you say create a few structures. Like here we have shown 3 structures with different periods. As I said previously, we can manipulate the period of a system, and we want a simple system because we want to run it many times. We can manipulate the period by changing the stiffness or mass or both of them. So here we have created 3 systems with 3 different periods. We use our numerical integration computer tool SAP 2000, and we like build up the response of interest. Maybe our response of interest is acceleration or displacement or something. And we find the maximum response through the earthquake. So for T1, we found R1. That's the maximum response. For T2, we found R2, and for T3, we found R3. And we do a lot more. And we build up the maximum response curve that we call it the response spectrum. Now you have a curve of maximum response of the structure, and it's a very useful tool in design, analysis and design, as we will see through this term. It's a standard way of characterizing ground motion and its effect on the structure. So that's the best curve that structural engineers used to like, and they still like to see what is the response of the structure, different structures to the same earthquake. It is a plot of maximum response of damped single degree of freedom systems with varying periods of vibration. So damped system was emphasized. So keep the damping the same for every curve. Damping of interest for response spectrum is normally 5%. So all these structures, they have varying period, but they all have like 5% damping. And this curve, it would be related to 5% damping. Normally, we create a spectral displacement, a spectral velocity, and a spectral acceleration. The third one is the most important one, which is of interest in structural engineering. First one is also important. Second one, not as much. So these are the typical spectral acceleration plots that you can create with the methodology that I explained. I think they are identical. However, we have used the logarithmic scale for this one on the right. Sometimes it's better because it widens the periods of interest in a lot of the structures, and where the curve also varies a lot. So it's like that we have a lot of variation between 0.01 and 1, and this one in this presentation on the right has widened those areas, while this presentation is narrower, so you cannot really find it or see the changes between 0 and 0.5. Now, as I said, we do that. We create different curves for different damping values. And as we expect, when we increase damping, the response decreases. Damping is like dissipation of energy. We allow more dissipation of energy, and the structure moves less or have a smaller acceleration on top of it with the same earthquake. So that's as expected, but we create different curves for different damping values. say steel is about 3%, 2%, 3%. So it's if you have a steel only structure, you're on the higher side. Concrete would be more like 5%. If you have other mechanical damping, etc., then you may have like 10% to 20% damping, which will reduce the response of the structure substantially, especially for stiffer structures. And so again, redefinition of the period, time for a structure to complete one cycle of vibration, which we already discussed. And again, this golden law of period, that when mass to stiffness ratio increases, period increases. So you increase your mass, you have a higher period structure, or you reduce your stiffness. And developing the spectral response, you just change that period and you read the response at different periods and plot it. Then you have the maximum response or spectral response. Discussion on damping ratio, which, as I said, every curve is also related to a damping ratio. Damping ratio is expressed as a percentage of critical damping. And a lot of times when you receive a single plot of, I think, a lot of time when you receive a single plot of spectral response, you should have the default of 5% in your mind. Like within the industry and NDCC, etc., the default is 5% for creating a plot. But most of the time we write on top of it or by each curve that this is 5% or 2%, etc. Effects of damping increase as connections loosen and structural members deform. So these are the phenomena that increase the dissipation of energy, and therefore they cause more damping. So going through this table, a typical table, I'm not saying that this is like, don't use it for your future consulting project, except it's exactly approved, but typically that's what happens. For welded structure, which has gone as far as half yielding, the damping level is at 2-3%, where you don't really expect nonlinear behavior. Similar case for reinforced concrete, 3 to 5%. Bolted or riveted steel, 5 to 7%. So when you have a bolted or riveted steel, there's more movement, and that frictional movement, it's damping energy, dissipating energy. Therefore, you have a higher damping percentage or damping ratio. I should call it typical damping ratio. For welded steel, the same scenario as the first one. However, for pre-stressed concrete, which is tighter and it causes less cracks, or highly reinforced concrete, where you also have less cracks. But however, now we have pushed it up to here, like the earthquake was so strong that it's pushed up to a steel yielding. Then you have about twice as much damping. Again, as we said here, when you have more movement, getting close to yielding, or when you have connections like in riveted steel, where there is like frictional movement, then you damp more energy. So similarly, when we get closer to yield and failure, we are damping a lot more energy. Almost, you can see in each case it's like twice as much as when you have smaller force in a way and the structure doesn't get close to yielding or failure. Again, the idea of maximum response, more described in a picture. You want to build up this curve. We are still in the process of building this curve. You have your earthquake that is happening, and there's ground acceleration with time. That's what is given to you, say, by geologists. And you know that in your region, that is the ground acceleration that you expect. You feed it into your SAP 2000 model, and you read, like at the roof of your single day model, you read a structural response. So this is your structure. You use SAP 2000, you make a model, you read the maximum value of a structural response, and this value for T1 comes here, and you plot it here. You put a point here, and then you create your structural response or maximum response or response spectrum. Deformation, response spectrum, procedure. Again, walking through the procedure one more time with a little bit more details for a more worked out example. You want to create the response spectrum for El Centro ground motion. This is the El Centro ground motion, which is acceleration calibrated with G gravity. The acceleration is changing between less than, like the PGA, what we call PGA, peak ground acceleration is less than 0.4. And you want to create the deformation response spectrum. Those three structures that we were talking about, you create three of them, 1 degree of freedom structure. All of them have 2% damping. So we are creating our spectrum for 2%. And by changing the height, which is a stiffness, or by changing the mass, we create three structures, one with the period of 0.5, 1, and 2. And we said that the spectrum is developed for 2% damping. Now, you feed these three structures even as simple as shown here. It could be like 1 degree of structure, freedom structure. You create this model in SAP 2000. You apply this ground motion, and you let the program run the analysis. For the first structure, the maximum, and we need when we say our maximum, we said we are talking about maximum absolute value, so positive or negative. The maximum deflection or displacement in the first structure was 6.79 centimeters. Here, we come here. Tn is 0.5 second. Deflection was 6.79. Then we go for the second structure. If it's me, in order to be faster, I only change the mass, because you just change the value of mass and the period changes. And for the second structure, the maximum deflection that I read is 15.15. Put it here. For the third structure, it was 18.96. We put it here, and you put a lot more points, and you create your own displacement spectrum. But however, there's another good news that SAP 2000 internally does that for you. If you find it through the menu, you can just say what your acceleration is, and the program will probably run it. Because it's single degree of freedom, it's much faster than what you think. So the program just run it 100 times, and in a millisecond, it will produce this curve for you. But you can do it one time try yourself or do a spot checks. The program creates this for you, and then you do a couple of spot checks to make sure you know what the program is doing for you. Now, moving on, say, I mean, traditionally, the computer resources were even more limited than that. To even run as 1 degree of freedom system was a little bit time consuming, maybe, and calculations was time consuming. So we have made it even simpler. So instead of creating the acceleration spectra or velocity spectra, we just create the displacement spectra as we just described. And there are these two equations to basically change displacement spectra to velocity spectra and to acceleration spectra. But because it's not exact, there's some like inaccuracy. We call them pseudo acceleration, and we call them pseudo velocity, because it's not really like this is not exactly the maximum acceleration, but it's very close to it. So it's pseudo acceleration spectra and the pseudo velocity spectra. Through this process, you build up, or the computer program does it for you, SAP 2000 does it for you. You create the software creates the displacement spectra, and velocity and acceleration is calculated based on that. So again, emphasizing not identical with the corresponding maximum response. However, they might be close. And then if you look at Chopra, it discusses like why we say might be close. Sometimes they're not too close, but that's an accepted solution in the industry. And yeah, this plot is like really old school, but that's what they used to do in all the books. They wanted to, in a way, combine these three plots into one. Therefore, they had this innovative way of using, first of all, you should use a logarithmic scale in perpendicular directions. And sometimes, I mean, in a very innovative way, they show all three spectra in one plot, which is nice. It was popular. It was, if you find all the reports, that's what they had. They show the spectra in one curve. So this was for L-central ground motion. Damping ratios between 0 and 20% are shown here. So the highest response is obviously 0% damping, and 2, 5, 10, 20, because the higher damping results in lower response. And if I still can do it correctly, because it's something that you basically only see in books right nowadays, you want to know what is your response at 0.03 with 0% damping. So you go up, and pseudo velocity is this. So it looks like it's something between 2 and 3 centimeters per second. Then the same if you go perpendicular to pseudo acceleration. You can read the pseudo acceleration for the same criteria. So it's something between, I think it's between 1 and 5. So you should be carefully be able to read it here. Again, going in this direction, you hit the deformation curve, and the deformation is much smaller than 0.1. So it's a very nice presentation that was popular. And it helps with understanding of the process. Now, yeah, sometimes say you are working in the industry and then you realize that your geotech colleagues, they talk a lot about frequency content, and structural engineers talk more about response spectrum. Basically, the frequency content is the Fourier amplitude of the motion. So they perform a Fourier transformation and they obtain the amplitude of the harmonics. And then they can have, like, sometimes it's required, we ask them to do a spectral matching, which means that they should modify certain response for the frequency content at certain frequencies, and then do a reverse Fourier transform and give us a motion which is slightly different. That's obtaining frequency content. Response spectrum, that's what I just described in the previous slides. Both of them have indication of what are the important frequency, which frequencies are more important. But other than that, there are different procedures and used for different reasons. End of this session or sub-session. So questions and discussions. Oh, I'm seeing that. Sorry, I was not paying attention. David and oh, it's from Von Abrego. I think it didn't show up. Yeah, okay. That's a good time to get back to discussion about the projects. How many people are allowed in our group for the project? I suggest that we use 3 people, or you be 3 or 4 people. Highly recommend that. I already told other teams that if they are like, you are a team of 5 and you know each other and you want to work with each other, go ahead, create a 5-member team. But you are creating a work plan first, and then your work plan should be convincing in a way that there is enough work for 5 people. So you should be able to prove that you keep 5 people busy with that project. So generally, highly recommend 3 or 4. If you are 5, I already told some people 5. Okay, we can live with it, but prove that you have enough tasks for 5 people. Is the work plan draft due on May 21st or 24th? 24th, yeah. So let's see. Doesn't go back. Anyways, yeah. Change the slides. Anyway, we can figure it out. Okay. Go back. Okay. Yeah, I'm always in favor of the easygoing interpretation. So here I said 21, 24, easygoing interpretation is 24. So yeah, 1 till 24. End of next week. Yeah, please do it by end of next week, and you will feel good that you know what you want to do and you have planned your workload for this course. Did I answer your questions? Is it okay, David and Jab? Already. Okay, any more questions about the schedule, outline, what we were just discussing, and single degree of freedom?
Sorry, just a quick question about the topics. Are we free to choose any of those topics there? Like, do we have to make sure other groups aren't doing the same topics? I'm not sure if you already touched on that. Thank you.
No. I mean, no, probably I didn't talk about it. Thank you for bringing up this. No, if you are like designing, even both teams are designing, say, a concrete high rise. It shouldn't be identical concrete high rise, obviously, but yeah, no, two teams or 3 teams can have concrete high rises, but different locations and yeah, different. Yeah, so there should be different concrete high rises. Yeah, right. Was it? Yeah. Did I answer your question? Or is it your concern?
Yeah, that's good. Thank you.
All right. Okay. Yeah, I mean, basically, a lot of times in similar courses, the teacher just says design concrete high-rises. But so you guys have a lot more choices. But it's fine if 2-3 teams are doing concrete high-rise or steel high-rise or bridges or other things that like structural engineers find attractive. Already, any more questions about this and first or second slideshow? Okay, we can walk into some single degree of freedom examples. Okay. Sessions, nothing. Yeah, so that's what I added one slide last year to this part. I know that you guys have gone through some static analysis courses, and I just wanted to, you have this slide available that you can refresh yourself on the slope deflection relation. It's a neat idea, and although we are using computer modeling a lot, at this minute sometimes to double check something or make sure that we didn't have a wrong input to our computer solution. So that's one of the neat things in structural analysis that we should have handy, or we should be aware of. We should be able to find it in books or these days on Google or ChatGPT, etc., and use it at least to double check the computer modeling. So the left side one is when you have a beam and it's like fully constrained on one side and you give it a rotation of 1 on the other side, the expected reactions on the two sides in terms of moment and in terms of the shear force. So if I can emphasize anything here, so just maybe have this table in front of you to double check, or sometimes for basic calculations. And the second one is, what if I have a beam element fully constrained on both sides, but one side moves by a unit of 1 in your system of units, whether it's meter or inches or centimeters. What are the reactions in terms of shear force and moment? And then traditionally, structural engineers were able to and should still be able to, for checking and reviewing computer models, to combine, like see every movement of their structure as a combination of these two movements, and therefore calculate the end moments and shear forces. That's a very basic and important concept in structural analysis, which is called slope deflection relation. So example number 1, in order to go to the important ideas that we discussed, this is not exactly dynamic, but we want to know how to refresh ourselves on how to calculate the lateral stiffness of a frame. Here you have the frame you have, which would be a real building with different stiffnesses for columns and the beam. The width of the structure is given to you and the height. And here are the representative degrees of freedom. So we expect different rotations on the two sides, and also one sideway deflection. Vertical deflection was not of interest to us because normally columns are pretty stiff for longitudinal deflection, also the beams. So we assume that deflection of the two ends of the beam are almost identical. Now, if we go through we want to calculate the lateral stiffness for the frame. And as I said, the elements are axially rigid. So we know that if we have a unit deflection, like to the side, based on the slope deflection relation that I just showed to you, you can calculate what is the moment that is created at the ends because of the unit moment of the column. Like this is column only movement. Beam has not really deformed by much. And also, so that's the stiffness. So if you have a unit movement here and your beam is very rigid, that's the level of resistance that you will have to provide. Like you should apply a force of K11 and basically the two moments at the joints. And now, if you want to only have deflection, rotation on one side, for each rotation, you should provide the stiffnesses, like force equivalent to the stiffnesses that we have shown here. And therefore, after going all through that exercise, I think I repeated this picture here, you can create the stiffness matrix. Again, this is something that structural engineers are familiar with through a structural analysis course. And you can build up a relation between all degrees of freedom and corresponding forces. But however, because we are only interested in lateral force versus deflection, therefore, we apply some lateral force to the structure. We are not obviously not providing any of these moments. And this is a matrix relation between forces that we want to provide, lateral force, no moment, and deflections. And I remember that here we have shown U1, U2, and U3, but U1 is really displacement, U2 and U3 are really deflections. Now there is this idea of a static condensation. Maybe we should at least be familiar with this term because you will come across that in some structural analysis and dynamic analysis. Why? Because say you don't have rotational mass, so you are not really interested in rotations. You are only interested in lateral displacement. And the idea behind a static condensation is that to get rid of these 2 degrees of freedom, which we are not interested in. Here we have enough equations to do that. So we already know that the forces in those 2 directions are 0. We just simply use that fact and we calculate U2 and U3 based on U1. I'm just trying to walk through the high level concept. I know that you guys are able to just do the detailed calculations on your own, but the high level concept is to get rid of these 2 degrees of freedom, and we take advantage of the fact that the forces or even the inertia forces, where we are interested in the dynamic forces in those 2 degrees of freedom, we are confident that they are 0. Therefore, we take advantage of that fact and we use these 2 rows of equations to calculate U2 and U3 as a function of U1. Therefore, now we know what is U2 and what is U3 as a function of U1. We inserted in the first equation, like this matrix equation basically is consisting of 3 equations. We use the first of the 3 and then we back calculate a relation between force, any lateral force, and any lateral deflection. So the outcome of this process was that we calculated the relation between linear relation between force and deflection. Now the question was, what is the lateral stiffness of this frame? Is force divided by deflection. Now, in terms of numbers, we obtain 96/7 EIC over h to the power of 3. So that's the lateral stiffness. This is the process. Yeah, I mean, I know that none of us will be using it a lot in long term, but that's something to be aware of and be able to find it and reuse it if you want to double check a solution. So based on the slope deflection, you get the stiffnesses involved in your system. You create your stiffness matrix. And I mean, static condensation looks like a fancy word, but then all it does is that because we are confident that the forces in certain directions, in this case, the rotational direction, are definitely zero. There is no inertia in rotational direction. We take advantage of that and we simplify our matrix. Basically, we had a 3x3 matrix. Now we have a single value, which is our stiffness. Now we know, like if you want to use the single degree of freedom system solution, you have the mass at the roof level. In a structural engineering, different codes, normally what we do, we say the roof mass is the real roof mass plus half of the column or wall masses. So you have the stiffness, mass is even easier to evaluate, and you use those values for simple, basically 1 degree of freedom calculation if needed. Now here, we want to just build up more, go one step further. Say here, I mean, say going back to example number 1, if we wanted to go further and get the period of this structure, at least based on hand calculation, as I said, we had the mass, we have the stiffness, and we have the equation put out of book, but I know that what I know is that mass is on top and the stiffness is on the denominator, a square root. But you put it out from your book and you get the period of your structure. Sometimes that's something that I will be repeating too many times, but you do your computer analysis and you're happy with it, but then I say, let me do a back of envelope calculation. I have the stiffness and the mass. This is the period of my structure. Now, what does the computer program says the period of the structure is? And then you compare, and sometimes you are surprised that they are very different, and you find some bug in your solution or a typo in your input. Very beneficial. Okay, now this is repeating the same exercise. We want to obtain the period of vibration of a bridge. So we have a bridge on 4 supports. So basically there are abutments and supports, and there are 2 bends. Normally in bridge engineers call this type of support a bend. I don't even know what the background of that naming is, but it's basically a few columns and a beam on top of it, or a girder on top of it, and the bridge deck sits on top of that. So it's the side view of this 3D picture. Each one of these is a bend. So we have 2 bends, and each bends have 3 columns in them. Bridge engineers are very interested in that, but yeah, I have the experience that even in engineering world, I was using the word bend, and some non-bridge engineers, they were concerned, what do I mean, what is bending? So, so I mean, it happens even among the engineers that, structural engineers, that one group doesn't totally understand the terminology of the other group. Abutment versus bend. So we have two bends and two abutments. The mass of the bridge is given to us. That's mostly from the deck. And you can also add half of the columns, as I was saying. Each bend column, so there are 3 columns per bend. And for each bend column, the I factors are given to us. The same in both directions. So as you see from this picture, I think they mean to have X as vertical. So the vertical direction is X. And in 2 horizontal directions, it's the same. So let's say it's circular or a square. It has the same, basically the same stiffness in both directions, both horizontal directions. The plastic modulus is also given to us. Now moving on, we try to obtain the stiffness of the band. So the three are identical, and we are not too concerned with directions. The 2 directions are the same. Again, you should be able to quickly find this in your books, in your structural analysis books, or web, or I don't know, ChatGPT gives that to you. What is the typical stiffness of a column? And you can find this. This is used a lot, so you should be able to recognize it. At least for myself, I'm still a person who uses the web a lot, but I say because I know this, I recognize it. So if a website or ChatGPT tells me it's 3 I over H, I say no, that doesn't look familiar. So you need the expertise, but then you use the tools, and you know the difference between correct and incorrect. The importance of expertise remains the same. Again, so you have 3 columns. Each one has this stiffness, and you add them up together, go through the number calculations, and you get the stiffness of the whole bend, consisting of 3 columns. So now for, I think we should call it longitudinal, so it's like along the bridge. You have 2 bends, and each bend had 3 columns. So you are seeing the effect of 6 columns in longitudinal direction, and you calculate the total stiffness of your system. And you already had the mass. Again, you are the expert. You type in your ChatGPT, gives you this equation. You look at it and say, okay, it looks okay, because I know that mass should be direct effect, and the stiffness should be inverse effect. And yeah, then you use the equation, and now you have the period of your system. So your bridge has a period of 0.57. So I assume that you guys can, quicker than me, just run this equation and get the stiffness, period of your system. Now moving to the next level, torsional stiffness. Torsional stiffness is especially important if we will see it. I think we will focus on this when we have a short session on timber, that the distribution of seismic load between columns varies like if you have rigid slab or you have soft slab. If you have soft slab, what happens is that, say you have a lateral force here, and you can just divide it proportionately between your 4 columns. Like each one of these 4 columns is picking up 1/4 of the force. That's a good engineering judgment. However, if you have a rigid slab, then the rigid slab might dictate rotation, might cause everything to rotate because this slab doesn't give in to rotational force. The soft slab will give in to rotational force, so it doesn't really cause some more effects. But the rigid slab just rotates and then pushes everything to rotate. So we will go through this like more as an engineering problem than we are doing the timber session of the course. Now, as a dynamics of a structure problem, we are interested in the torsional rigidity of the system. And basically, mass of the slab is m, and each column has a rectangular cross section. We don't even assume that ix and iy are the same, so they might be different. If it's a square, they are the same. Going back again, 12 ei over h to the power of 3 repeats itself. So for each column, we can calculate the stiffnesses in the two directions. Now, if you want to just using the basic concepts or engineering judgment to see what is the rotational stiffness or torsional stiffness of this structure. This again goes back to structural analysis. What you do to fully understand it and do it correctly is that you give it a unit rotation, you give your structure a unit rotation, and then you will look at the response of your structure, how much resistance is there. And the resistance to a unit deflection is the stiffness, basically. Here we repeat the same exercise. We rotate this slab, which is connected to these columns. We are looking at the plan view. We give this slab a unit rotation, and then we measure the deflections. So this is rotational deflection, but because this is very rigid, it has pushed this point to the side by b/2 and to like up by d/2. All right, so go back. You see it's d multiplied on one side and b on the other side. And I show, we should have shown b and d here, because here it looks very squarey, but it's not really exactly a square, it's a rectangle. And so that's the basic geometry. You see that this point has moved b/2 to the top, to like up, and d/2 to the left, and therefore it sees this much resistance in the two directions. Similarly, for all four corners, we can determine the resistance. And then we want to use this resistance, like they are, you see, kxd/2 is exactly the same on the four corners, and kyb/2 is exactly the same on the four corners. This is force multiplied by the arm, which is again, for this one is d/2, is the moment. So at each corner, we have a force of kxd/2 force multiplied by the arm, which is again d/2. And there are four of them. So that's the force or torsional force that we need. And then similarly, we have four torsional moments or forces or moments, we should call them moment in a way. Kyb/2 multiplied by b/2, and you have estimated your rotational stiffness of the system. So basically, yeah, that's also a good exercise mostly in analysis of structures, but that's an important step. If we want to do dynamics, we estimate our stiffness and we have the mass, and then we can go next step, calculate our period, what we did here. Here it was longitudinal deflection. Here again, we had like a structure deflection sideways. We got the stiffness here. And masses are sometimes easier to just approximate the mass assigned to a certain direction, like total mass of the deck and half of the column here. Probably rotational mass is a little bit more, slightly more sophisticated to calculate, but it's not too difficult. So you can get your rotational mass and you have your rotational stiffness. Again, you can hand calculate your rotational period to start with. But we stop here, we jump into a different example. Here's a shake table solution. I think I copied it from Chopra last year, but it has a lot of similarities to what we want to show you on June. We're running out of time as well, but we finish this and then we go. Just emphasizing, and I will send the email that there won't be any class on on Tuesday, June 4th, there's no class. Friday, June 7th, we have a 3 hours class inside university, and attendance is again mandatory. Part of that will be showing the shake table, U-week shake table. This is similarly a shake table in University of California at Berkeley. The structural number is plexiglass, and a smart shaking table similar to what I know UVic has. Say we can do some tests, we will do same thing, we try to do the same thing at the class, shake it a little bit and then leave it without any forcing function. The deflections will decay through the time. So that's a decaying free vibration after the first shock. We record the level of deflections at different time steps and the number of peaks that are in between. So between time equal t equal 1.11 and 3.844, we had that's peak number 1, that's peak number 11. I would say there are 10 back and forths in between. And we have the value of the peak, which is in terms of acceleration. So because there were 10 back and forth, the period could quickly be estimated in free vibration. Basically, the change in time divided by 10 back and forth, your period was 0.273. I have shown you this solution for decaying a free vibration and how much the response changed in 10 steps, dividing by 2 pi and then dividing by 10 because there were 10 vibrations in a way, and a very quick and good estimate of the damping of the system in this example. We can, next time we will, because it's already 12:20. So this is the free vibration, quick estimate of period and damping of the system. Next time we will proceed to harmonic excitation for the same example. Now, feel free to ask your questions, and hopefully you have enjoyed this session. Thanks a lot. I'm seeing that some people are leaving. Feel free to leave. Have a nice rest of the day and have a good weekend. I will talk to you on Tuesday. I'm staying for one or two more minutes in case anybody has a question. And I'm looking at the chat.
Thank you.
Thank you, and thanks for that.